morning, good afternoon. It's a pleasure to be here to have the chance to speak to you today. So the search for liquid water on planets other than the Earth inspires both professional astronomers and citizen scientists alike. A lot of this interest is fueled by the hypothesis that liquid water is an important ingredient for habitability. In fact, the habitable zone for a planet orbiting a star is often defined as the range of orbits on which an Earth-like planet could harbor a liquid water ocean on its surface. But what about planets that aren't so Earth-like? What about planets that are more akin to mini Neptunes, with voluminous envelopes of light gases? In what scenarios could those types of planets harbor liquid water oceans on their surfaces? Well, that's a question that's captivated my interest, and effectively I want to explore with planet interior structure models and planet climate models a range of scenarios on which a sub-Neptune planet with a voluminous gas envelope, hydrogen-rich gas envelope, could harbor a liquid water ocean. And I want to place constraints based on observable exoplanet properties, mass, radius, and orbital periods, to constrain the parameter space where liquid water oceans might be possible. So this is my ultimate goal, and today I'll be discussing or telling you about some of the work I've been doing moving in this direction. But first, I'll give a bit of an introduction to kind of Neptune size and smaller exoplanets before moving on to the meat of my presentation, constraining scenarios for liquid water oceans, and then conclude with a couple of case studies. Okay, so let's get started.
Is there a reason to limit it to sub-Neptune? You know that it's Jupiter like other economic.
Well, if the planet's Jovian size, then it would need essentially too large of a hydrogen envelope to have pressures at its surface low enough for like a liquid water ocean. So I'll kind of get into that a bit by the end of my presentation. Okay, so exoplanets and round distance stars are now giving us examples of planets in the size range between the Earth and Uranus and Neptune, for which there are no analogs within our solar system. Now, we can't send a probe to these exoplanets to study them directly, but there are many ways to detect them and to characterize their properties, and I'll describe a couple of the more prolific front-runner techniques. So, by observing the dynamical effect of the planet's gravitational pull on the orbit of its host star, we can get a measure of the planet's mass through this radial velocity, or stellar wobble technique. Now, if the planet's orbit is serendipitously aligned with respect to us here on Earth, so that we see the planet pass in front of its star, by the fraction of the light that the planet blocks, we can get a measure of the planet's size in relation to the size of the distant star. So from this transit technique, we can get a measure of the planet's radius. Now I just want to return to this image that I started with, and I'm wondering, does anyone recognize this constellation? So this is about 40 degrees by 30 degrees. And it's a little bit of a trick question, actually, since this is a 30-minute exposure with a 15-millimeter camera. There are far more stars here than you'd actually see with the naked eye. Any guesses? No, that's a good guess, though. It's actually Pegasus. And I chose this one because, well, the first ever discovered radial velocity exoplanet, 51 Peg, is somewhere around here. And actually the first transiting exoplanet, HD 209-458b, is also found in this constellation. Now those first exoplanets discovered by each of these techniques were Jovian-sized, Jupiter-sized planets. But we're now finding Neptune planets that are Neptune size and smaller. And actually we're finding them in abundance. So from radial velocity surveys, for instance, this ADA Earth survey estimates that an occurrence rate of about 12% for planets in the mass range between 3 and 10 Earth masses on orbital periods less than 50 days. Now, the Kepler Transit Survey, in their data release last February, nearly 3/4 of their planet candidates were smaller than Neptune. And Howard et al. 2011 estimates an occurrence rate of roughly 13% for planets between 2 and 4 Earth radii, again on orbital periods, less than 50 days, based on this Kepler data release. And then microlensing surveys were some of the first to provide hints that Neptunes were common, even though they're sensitive to planets further out from their star on longer periods. But it found that beyond the snow line, Neptune-mass planets are at least 3 times more common than Jupiter, the 95 planets. So microlensing, radial velocity, and transit surveys are all starting to give a consistent story that these smaller planets, or the planet abundance increases toward smaller masses and smaller radii. But what are these Neptune-sized planets? Well, for that, the subset of planets that are detected both through radial velocity and through transit, for which we have both a planet mass and a planet radius, are especially valuable. With both the mass and radius, we have a measure of the planet density and can start to constrain the planet bulk compositions. To date, there's more than 200 exoplanets known that have both measured mass and radius. And I'm plotting them here on a mass radius diagram. So here is planet mass in units of Earth masses on a logarithmic scale, while the y-axis is planet radius in units of Earth radii, again on a logarithmic scale. And each of these colored curves are mass-radius relationships from Seeger et al. For kind of illustrative compositions to help guide your eye. So the solid blue line is for 100% pure water. The solid red is for pure silicate, a pure kind of rock planet. And the one, this purple line is for 100% fire planet. And so these are the hot Jupiters, some of the first planets discovered. But in this talk and in my research, I'm mostly interested in these smaller guys. And so here we are zooming in. So these axes are now on, again, planet mass, planet radius, but on a linear scale with the same mass radius relation. This dashed red line is for an Earth-like composition. So an iron core accounted for about 32% of the planet mass, surrounded by its radius. Okay. But mass and radius is not the whole story. We also have information about the amount of radiation the planet is receiving from its host star. And it's parameterized in terms of this equilibrium temperature parameter, which I'm showing here on the plot now with the color scale of the various points and the legend shown up here. So the amount of radiation received from the star governs not only affects not only the thermal evolution of the planet, but also affects the rate of mass loss of any volatiles. Okay. So this is essentially the information that we have about these planets. And then what we do is use planet interior structure models, use models to interpret planet mass, radius, and equilibrium, and orbital period, or equilibrium temperature measurements to constrain a range of possible ball compositions. So we'll move on to just briefly summarize the planet interior structure model that I use. Okay, so I consider spherically symmetric, fully differentiated planets in hydrostatic equilibrium. I allow for several different chemical layers, with the more dense layer being at the center. So a metallic core, silicate mantle, possible water or ice layer surrounded by a gas. And I parameterize the energy budgets of these planets with two parameters. This equilibrium temperature that I described before, which parameterizes the incoming radiation from the star. And then this T sub int, so this intrinsic luminosity parameter that parameterizes the intrinsic luminosity of the planet. So this would encapsulate both any radiogenic heating in the planet interior, as well as any leftover secular cooling from the planet formation. So I want to emphasize that this T sub int doesn't actually represent temperature at any point in the planet, but rather the Stefan-Boltzmann constant times T sub int to the 4 is the energy flux coming from the planet interior into the planet envelope. So effectively, I'm solving the equations in stellar structure, but applied to a planet. I'm considering planets with envelopes in radiative convective equilibrium. So where the envelopes are convectively unstable, I'm using this an adiabatic temperature profile. And then for a photospheric boundary condition, I'm using this generalized version of the Eddington atmosphere, which is an analytic solution to semi-grade two-stream approximation, equations of radiative transfer from Guillot 2010. So this first term is just the familiar Eddington atmosphere, and then the second messy term just accounts for absorption of visible light coming in to the planet atmosphere. Yeah. So gamma is the ratio of the visible optical depth to the infinite. Okay. And so that's how I treat the temperature profile in the gas layer. In the rocky layers, thermal effects, like the iron and silicate layer, thermal corrections only have a very small effect on planet mass radius relation, on the order of 1%. So in the iron and silicate layers, I'm actually taking constant temperature equations of state from Seeger et al. 2007. Well, for the water, I take a combination of NIST steam tables, density functional theory, as well as atomic spin-Dirac equation of state. And for hydrogen and helium, I use Sonom et al. Yeah.
So is that gamma, that's a single gamma for the whole model that's evaluated at some characteristic temperature density?
Yeah, so it would be evaluated at characteristic conditions in the upper layer. Yeah, so this is, the Guillot temperature profile is essentially the upper boundary condition. And so with this model, essentially, I wanted to try to, when constraining the interior composition of an exoplanet, I explore for the measured mass and radius how the mass within the planet can be distributed among these chemical layers within the planet and still agree with the measured planet radius. But as you can imagine, here I have 4 chemical layers within the planet, and really only 2 observational constraints, the measured mass and the measured radius. And so this problem is under-constrained, and there's a degenerate space of potential compositions that can fit the measured mass and radius. And this is what I'm illustrating here. So, yeah, you don't have to worry about necessarily understanding this diagram for the whole rest of my presentation. But essentially here I'm showing on a quaternary diagram the range of possible compositions for this one example transiting exo-Neptune, GJ426. And so each corner, each vertex in this diagram represents a pure homogeneous composition. So this upper vertex would be a pure hydrogen helium gas planet. Here, this vertex would be a pure water planet, pure iron planet, and pure silica planet. And then the perpendicular distance from the vertex to the opposite face gives the mass fraction of a composition of that particular component. So this is just a convenient way to plot 4-component data that must sum to 1 on it with each component totally density. So this surface represents kind of a whole range of different compositions that fit the nominal measured mass and radius. When we take into account the observational uncertainties as well as uncertainties in the energy budget of the planet, this spreads into a full volume of possible solutions.
What's the color of the
So the surface is colored according to the mass fraction in the hydrogen helium gas layer. So for this planet, for the nominal 0 sigma mass and radius, the amount of hydrogen ranges from about 3% up to about 12%.
So key is constrained from the fifth fill as well. That's not an extra parameter.
So it is effectively an extra parameter. Yes.
It's
So
not
here I've just picked a nominal value to show. Yeah. But yeah, that can be an important source of uncertainty for these small planets with gas giants.
Can you give us some feeling about how different the density is for those bottom 3 components? So each row is always around 1 or 2 grams per cc. In terms of bulk density?
In terms of bulk density, well, there are compression effects as well. Okay. So effectively, every composition on the surface, the mean planet density is the same. Yeah.
These are constrained to fit the RNN.
Yes.
So you pick out a consequences.
Yeah.
Yes.
Right. I just want to say, if it's pure iron versus pure silicate, how different is the density?
I can go back to
Oh, okay.
this
sorry.
diagram. And essentially, so this is, yeah, the pure iron line and the pure silicate line. So it's,
50%.
yeah.
Thanks.
You mentioned silicates are like 3 to 4 grams per cc,
Yeah.
and iron 5 to 8 grams.
That is strong. Because iron there is just like pure, right? They're just like-
Yeah, iron's probably closer to 7. And then
There's some
So here's the observed low mass transiting exoplanets to date. And I just wanted to highlight, so that one example I showed on the quaternary diagram was a transiting, was more massive than Neptune. But I just want to highlight that there have been planets smaller than Neptune, smaller both in terms of mass and radius, discovered that nonetheless require substantial gas layers to account for their low main densities. And the nature and formation of these planets is still a very interesting question that's not completely resolved, but there's been a number of formation processes proposed, and I just listed these there. And so, actually, I think I've worked on a few of these. So, coordinated diffusion beyond the snow line, and Murray has also described potential in situ diffusion of Neptune-sized planets. And I guess I'll highlight an example of how these types of mass radius interior structure models can help to rule out potential formation scenarios. Essentially, ruling out the scenario where these planets formed as rocky planets that then outgassed a substantial envelope of light gases. So, and to rule out the scenario, I effectively just consider the most optimum case for outgassing a light envelope to see what is the maximum radius for an outgassed planet, rocky planet, that we could assume. So to do this, outgassing occurs in the planets formed from some combination of rocky material, potentially with added water, and then during formation, metals in the rocky material react with the water and oxidize, releasing hydrogen-rich gas envelope. So in general, a wide range of envelope compositions can be produced by outgassing. Here I'm considering a hydrogen-rich scenario in order to set a low density limit. And so by considering the most optimal chemical composition for the primitive material, sampling from the range of meteoric chondritic material observed in the solar system, and considering the extreme of 100% oxidation and 100% retention of the hydrogen-rich gas envelope, I can set with interior structure models a relatively strict upper limit on the radii of planets that acquire gas layers from this process alone. Here's what I find. So here are radius upper limits for outgassed rocky planets, hydrogen-rich gas layers, and this blue line is for an equilibrium temperature of 500 Kelvin, while this yellow line is for an equilibrium temperature of 1,000 Kelvin. And as you can see, there are a number of planets with radii exceeding these limits. And so effectively, we know that these planets essentially require a more massive gas layer that then could plausibly be produced by outgassing.
How do you decide how much hydrogen you can cram into the rock before it's outgassing?
So in this case, the limit is really set by yeah, and considering the limit where there was enough water present to fully oxidize the heat. So that's, and then some stoichiometry, considering the iron's completely oxidized, I can then derive an upper limit of about 1.8% by mass of hydrogen. Okay. So this illustrates how, even though there's a degenerate range of different compositions that can fit any given exoplanet, planet interior structure models can nonetheless lead to interesting insights into the planet bulk compositions and formation scenarios.
But if you assume, if you assume the hydrogen atmosphere actually may not be stable, maybe assumes it's stable,
Right.
would that, how much lower would the limit? Because these are really close to the stars, so you have strong
Right.
intrinsic state.
So, exactly. So, atmospheric escape processes would definitely be very important for these planets as well.
Do you know roughly how much lower you can really change the ranges?
So, you could decrease it if the planet loses all its hydrogen, it could go down to essentially be a naked rocky core, have a radius below the
You
sun.
haven't calculated.
So it's saturated.
Pardon?
You have not tried to calculate the human mass on the
I have in my recent paper with Peter Bonington and Jeffrey Sauer, and yes, some of these very low mass, low density planets have escape loss, envelope loss timescales of a megayear or less. So, yeah, so they would not be. But it's still okay. So now that was an introduction to planet interior structure models and to Sub-Neptune Exoplanets. So now I want to apply these interior structure models to explore scenarios where Sub-Neptune Exoplanets cover liquid water oceans. So first, let me review kind of the classical picture of the habitable zone. And so here, when people have considered liquid water ocean-known planets previously, they've mainly focused on terrestrial planets. So a carbon dioxide water atmosphere is typically assumed. So this encompasses both Venus, Earth, and Mars' atmosphere. So in this case, again, the habitable zone is a range of distances from a star on which an Earth-like planet could harbor liquid water ocean on its surface. So the inner edge is set by the runaway greenhouse limit. So there's an upper limit to the radiation flux that is saturated, a planet with an envelope saturated in water vapor can be radiated. And so interior to this planet, water ocean on the planet would be completely vaporized. Okay, and then the outer limit is affected by the condensation of carbon dioxide, which is an important greenhouse gas. Okay, so this is for carbon dioxide water envelopes. But actually, planets with hydrogen-dominated envelopes are appealing as well. For one thing, hydrogen on a low-mass planet can contribute significantly to the planet radius. So with larger radii, these super-Earth planets are more detectable. Furthermore, hydrogen-rich envelopes are more amenable to atmospheric characterization with transmission spectroscopy. So in transmission spectroscopy, essentially you're looking at how the radius of the planet observed in transit varies with the color of the light you're observing. And the scale of that variation is set by the atmospheric scale height. Planets with hydrogen-dominated atmospheres with low mean molecular weights have larger scale heights, with more, which then leads to more detectable spectral features in their transmission spectrum. Okay. So, given their high detectability and the better potential for atmospheric characterization, it behooves us to consider in what scenarios can a sub-Neptune planet with a hydrogen-rich gas envelope plausibly harbor a liquid water ocean on its surface. So I just want to draw your attention to two papers, one by Stevenson in 1999 and Gergenberg and Ridos in 2011, that made the point that hydrogen collision-induced absorption can allow hydrogen to serve essentially as a non-condensing greenhouse gas, effectively extending the habitable zone to greater distances from the star. Okay, so I want to take this a step further, again, and place constraints on the parameter space in terms of planet mass, radius, and the period where liquid water oceans may be possible. And again, just to highlight some of the differences in what I'm doing to compare to the classical view of the habitable zone, is that in considering hydrogen-rich envelopes, using interior structure models to calculate the contribution of the planet envelope to the planet radius, and also taking into account kind of a richer potential array of planet energy metrics. So for the terrestrial planets, the planet climate is really driven by the sunlight received, which heats the ground and then is re-radiated through the atmosphere. For planets, whereas on Neptune, its intrinsic heat flux is of a similar order to the irradiation it's receiving from the sun. So here I'm also going to allow for a potentially significant intrinsic planet luminosity in my calculations. Okay. So now, heading back to the model, I'm going to focus for a moment just on the planet envelope. And here, I'm exploring scenarios where at the base of the envelope we have a liquid water ocean. So I want the planet envelope to be saturated in water vapor here at its base. And so, considering the constraints of radiative convective equilibrium, as well as phase equilibrium of the ocean, we're going to constrain the combinations of T sub int and the equilibrium temperature to constrain the possible energy budgets that allow for liquid water oceans. Okay.
Do you assume water is mixed uniformly through the whole atmosphere, the same mole fraction?
No, I take it into account condensation, so I'll get to that in the next two slides. Okay. So first, to harbor so let me elaborate on what these two constraints mean. So in order for there to be a liquid water ocean on the planet's surface must have fall at pressure and temperature conditions where water is in the liquid phase. And so it's highlighted here on this diagram, which plots temperature on the x-axis and pressure on the logarithm scale here, increasing on the y-axis. So I want the surface of the planet at the base of the envelope to fall in this light green region in which water is in the liquid phase. And then, as the question alluded to, with the envelope saturated at its base so that the ocean is neither effectively evaporating or the envelope is neither effectively collapsing and condensing, But with a saturated envelope, I need to take into account variations in the water content throughout. Because the temperature decreases, the saturation pressure of water decreases. And so you get lower water mixing fractions at saturation. And that condensation of water can affect essentially the lapse rate of the AUMAC. So I do take into account variations in the, essentially inhomogeneous water content throughout the envelope and the moist AUMAC. Here I've written an approximation of the moist AUMAC for an ideal gas. Okay, and I'm taking, again, the same photospheric boundary condition from VO in 2010. Okay, and so with this, with these ingredients, to calculate the pressure temperature profiles through the envelope, and explore the range of combinations of intrinsic planet luminosity and the degree of radiation from the star that allow for potential solutions with liquid water ocean on the planet's surface. Here's what I find. For an example, with a surface pressure of hydrogen of about 100 times the Earth's atmospheric pressure, so 10 to the 7 pascals. And so shaded in blue are the combination of intrinsic temperature here on the y-axis and equilibrium temperature on the x-axis that allow radiated, essentially solutions for the pressure temperature envelope for a sample choice of surface gravity of 10 meters per second squared. So the surface temperature in this plot increases in the surface from this inner edge towards the outer edge. So cases out here are essentially too hot for liquid water oceans on their surface. While down here, they're too cold. And the water mixing ratio in the envelope increases, again, as the surface temperature increases and the saturation vapor pressure increases. Okay. We can do this for other choices of the surface pressure of hydrogen. So for lower surface pressures, we get we can have higher intrinsic luminosity fluxes, intrinsic temperatures, and the opposite for higher surface pressures of hydrogen.
What's the effect of T interior filter?
Pardon?
What's the T internal filter?
It would be about 35. Yeah. Yeah, but so these calculations are more targeted towards planets with essentially optically thick gas envelopes. So for the Earth, the surface has a larger climate. Okay. So here I'm presented essentially the range of equilibrium temperatures and intrinsic luminosity temperatures where liquid water oceans are possible. But this wasn't what I was, even though these are parameters that are convenient in my model, it wasn't my ultimate goal. I really wanted to constrain, to give the observational context to my constraints on the liquid water ocean. So, and describe the parameter space in terms of planet mass, radius, and orbital period. So, to do that, let's go back to the model, and I've so far just looked at the planet envelope to derive constraints from the planet energy budgets. And now, let's take a look at the planet interior and use, with some assumed interior compositions, planet interior structure model to calculate mass radius constraints for these planets with liquid water oceans. So we'll start with an illustrative choice of an Earth-like interior composition for the planet rocky core. So this is a mass radius relationship for just a naked core with that's 30% iron and 70% silicates. And then if I consider the upper limits to the radius of planets with liquid water oceans, hydrogen-dominated gas envelopes, this is what I get. So essentially, I've marginalized over the range of interior temperatures and of the range of plausible energy budgets from the previous diagrams that I showed. So this is an upper limit on the radii of planets with liquid water oceans above surrounding an Earth-like rocky core. But of course, I can choose different compositions for the planet interior. So with a lower density interior, now one that's 2/3 ice and 1/3 rock, these are the limits that I obtained. So the red line correspond to planets with an equilibrium temperature of about 550 Kelvin, while the yellow corresponds to an equilibrium temperature of 260 Kelvin. And then on this diagram, you can plot the current census of low mass transiting planets. So all the points plotted in blue are essentially far too hot for liquid water oceans. They have equilibrium temperatures in excess of 500 Kelvin. It's just these two little guys here in red with equilibrium temperatures of around 550 Kelvin that are straddling this upper limit.
So,
yeah.
I mean, the different models seem to not, at least for looking at it, they're not very different between a fair amount. How big is really the theoretical uncertainty in these models in the sense of how much would we be able to, and what would be from the theoretical point of view, what is the most uncertain input in the model? Maybe today would be the question right now.
No, that's an excellent question. And it's so the equation of state of the rocky and ice layers account for an uncertainty of about 30% or 3% or so on the radii of the interior layers. So I'd have to say that the most limiting assumption that I've made is probably assuming a very distilled composition for the gas layers of planets. Yeah, the fact that here I'm considering scenarios where it's a mixture of water and hydrogen, essentially. And so if I were to include, and I want to do this eventually to consider a broader range of scenarios, but the inclusion of even trace amounts of other greenhouse gases could have an important effect on the range of energy budget for these planets that allow for liquid water oceans. But here, I'm really just trying to consider extreme scenarios to place constraints on the parameter space where essentially liquid water oceans, you would not expect liquid water oceans. Yeah, but that's an excellent question. Okay. And so, yeah, I'll quickly wrap up with just a couple case studies to show how these models can apply. So first, I'm going to consider one of these little red guys here, this planet, GJ1214b. So this was actually the second discovered transiting sub-Neptune sized planet. It has a mass of about 6.6 Earth mass, so it's a radius of about 2.7 radii. And so it has a low enough density that it needs some sort of a gas layer to account for its low density. And there are many plausible or potential scenarios for formation scenarios for how this planet could have formed and for what the nature of its gas layer might be. These are three potential end members. A mini Neptune scenario where the planet has a roughly solar composition, hydrogen helium envelope, and in this case, its envelope would need to be between about 100% and 6.8% of the planet's mass to account for its radius. Also, the planet, a second scenario is if the planet formed kind of from a mixture of ice and rock materials similar to the comet, and instead has a very high mean molecular weight, water-dominated envelope. In this scenario, the planet, more than 50% of the planet's mass would need to be in the water layer in order to account for the planet's low mean density. And then the third scenario is one that I mentioned before, an outgassed rocky super Earth. And this is the one that requires the most fine-tuning, the most extreme kind of scenario in order to get enough hydrogen to account for the planet radius. So with this subcontext of there being kind of a wide range of potential scenarios for the gas layer of this planet, and there's been a number of measurements by groups here at the University of Toronto and CITA as well to use transmission spectroscopy to distinguish between these. So here, when we explore, under the assumption that the planet has sufficient, the planet has some sort of a water-rich envelope, in what cases could the planet harbor a liquid water ocean? And so here, on the temperature pressure diagram, I'm showing the liquid water phase diagram, or the water phase diagram, where here this highlighted yellow region shows the conditions where water is in the liquid phase. And this is a sample pressure temperature profile for GJ 1252. You can see by playing with some of the uncertain planet parameters, we can see how this pressure temperature profile is affected. So increasing the planet albedo, the amount of radiation that's reflected, we can decrease the slow pressure region of the planet envelope. Decreasing the planet intrinsic luminosity effectively changes the entropy of the planet interior. And you can see that we have to decrease TN quite a bit in order for the planet pressure temperature profile to intersect these conditions where water could be in the liquid phase. And we find that GJ 1252b would need a very low intrinsic luminosity in order to have a liquid water ocean on its surface.
That's just decreasing TN? It looks like if you do both, bigger, one quicker, you might get that more. Is that right?
Yeah, here I'm plotting some illustrative examples, but sample examples.
But how much is the variation in that from the lower to the upper curve?
I would have to double check what choices I plotted. But here, essentially, GJ1213b would need Tn of between 10 to 20 Kelvin. Yeah, again, depending on the albedo that I choose in order to test the water phase. And so that corresponds to an intrinsic luminosity per unit mass that's more than 2 orders of magnitude smaller than that here on here. So, so that already places, I think, an interesting constraints on the range of possible scenarios, just based on the thermodynamics of the planet envelope, where this kind of gravity acceleration. And again, we can see that from this diagram that I showed before. So out at equilibrium temperatures of 550 Kelvin, you can see the increase in Tf in the equilibrium temperature is offset by a decrease in the allowed range of intrinsic luminosity. Okay, so GJ1213b likely does not have a surface liquid water ocean. So the only scenarios where it could have very low intrinsic luminosities. And the same conclusion holds true for this other red point, equally red. Okay. And then I'll just quickly end with a second case study, briefly mentioned Kepler-22. So this was a planet announced last December, discovered by the Kepler Space Telescope. And it's the first transiting planet found in the classical habitable zone. So this planet has a radius of 2.4 Earth radii, but actually doesn't have a constraint on the planet mass isn't measured. The planet mass is currently unknown. There's a 3 sigma upper limit of 124 Earth masses. But if the planet had an Earth-like composition, its mass would be about 34 masses. And assuming an Earth-like albedo, the planet's equilibrium temperature is about 262 Kelvin. Given that we don't know the planet mass, and that the majority of, that all the exoplanets that we know of to date that have radii in excess of 2 Earth radii, and that have measured masses, are more akin to, or have low density, require a gas layer. You can see in what scenarios, if Kepler-22 is more like a mini Neptune with a voluminous hydrogen-rich gas layer, could it harbor liquid habitation? So here, I now want to draw your attention to these yellow curves that represent, that are for a Kepler-22, the equilibrium temperature of about 260 Kelvin. You can see, if I just plot 2.4 Earth radii here, that I can set essentially a lower limit on the planet mass that could allow for scenarios where Kepler-22 could have a liquid water ocean. So if Kepler-22b's mass is less than 6.2 Earth masses, essentially it would require too much hydrogen to account for the planet's radius to be able to harbor a liquid water ocean. Okay. So we don't know of any transiting sub-Neptune mass planets with liquid water oceans to date, but as more transiting planets are discovered, I'm very excited about filling in the mass radius diagram. And so here I'm plotting now equilibrium temperature as a function of the planet radius. And each of these crosses are the planets for which we have, transiting planets for which we have mass constraints. And these purple dots are the full sample of Kepler planet candidates. So as transit and radial velocity surveys push this sample of planets for which we know both the mass and radius down to lower radii and lower masses, the potential to probe composition trends between potentially rocky and volatile rich planets, I think is very exciting. Okay, and so I just want to summarize the main points I hope you take away from this, from my talk, and that is that there's this new exciting class of sub-Neptune planets, and that there are many possibilities for how these planets could have formed, but I illustrated an example of how planet interior structure models have largely ruled out outgassing, at least for the lowest density planets. I described how we can use climate and interior structure models to constrain scenarios for liquid water oceans and sedimentary planets, and highlighted how GJ1215b would need a very low intrinsic luminosity to have a surface liquid water ocean, while Kepler 22b would need to have mass larger than 6.2 Earth masses. And then as more and more of these sub-Neptune planets are discovered, I'm looking forward to studying composition trends to be able to hopefully map out the transition between rocky planets and planets with voluminous gas layers.
Thank you, Leslie. I think maybe we have time to do one or two questions.
For the planetary evolution model, do we have any constraints on the intrinsic luminosity from planetary evolution model?
That's an excellent question. Right now, in my models, I'm just keeping that intrinsic luminosity as a parameter. Because in effect, a lot of simplifications and assumptions that I can get away with when studying the mass and radius relationship for planets do come to bear when considering the thermal evolution. So there, the detailed chemical compositions have a larger effect. And so, yeah, that's definitely something I want to pursue. It's not something that I've included yet in what I presented today, but ultimately it could potentially further constrain the parameter space for liquid water oceans, but it would be more sensitive to assumptions about the precise chemical composition of the planet layers.
Well, just regarding your last point, potential for ensemble studies, we now have maybe quarter dozen Neptunes Earth which have measured radius and mass.
Right.
What kind of impression are we getting out of this dozen systems? Do we have any firm conclusion at the moment?
So at the moment, sorry, I in the interest of time, I can breeze through this. For the moment, most of the planets, the dozen planets known to date, fall in this regime where they need some sort of large volatile compound in order to account for their observed radius, their low densities. So the firm conclusion at the moment, at least based on what we've seen so far, is that planets larger than 2 Earth radii have substantial volatile contents or gas layers that contribute to their transit radii. As we move to smaller planets, so here the points I've plotted in blue are ones that have low enough density such that they need some sort of volatiles to account for their transit radius. The ones in where a rocky composition could account for the mass radius pair. So as you can see, as we really need to push to smaller radii in order to probe kind of the transition between rocky planets and moving.
But it does look like the low mass one are rocky, the high mass one is outgassing. Is that right? There's a radius. There's a radius, sure. But is it true that the low mass?
It's like the hot ones.
The hot ones to date are the ones that
Yeah,
continue
that's
to
true.
So there's a lot of observational biases as well, kind of interact in this current sample. So I think we definitely need larger numbers and a careful assessment of the observational biases that go into also selecting the populations in the study.
So this is going to be here for all of tomorrow. If you have any more questions, discuss it further. To have further discussion.